If you've ever chatted with an AI, let it write a paragraph for you, or asked it a question, you've already experienced the power of large language models. These machines are not just glorified autocomplete tools, they're shifting how we create, communicate, and even think. But before we get ahead of ourselves, let's break down what they are, why they matter, and how they evolved from clunky rule-based programs to near-human conversation partners. So, what exactly is a large language model? At its simplest, an LLM is an artificial intelligence system trained on massive amounts of text data. Its job? To predict the next word in a sentence. Sounds basic, right? Well, this simple mechanism, scaled up to billions of parameters and trained on trillions of words, becomes something almost magical. Think about it like this: imagine reading thousands of books, news articles, Wikipedia entries, and social media posts, all at once. Then, when someone asks you to write a story or summarize an article, you can recall all that knowledge instantly and generate a response that feels natural. That's essentially what an LLM does, except it's trained on far more text than any human could ever read in a lifetime. And because of that, LLMs aren't just reading text, they're learning patterns, structures, and even the subtleties of human expression. They don't understand language like we do, but they're incredibly good at imitating it. Why do LLMs matter? Sure, they're cool party tricks. Ask ChatGPT to write a Shakespearean rap battle, and you'll get something entertaining. But beyond that, these models are changing entire industries like medicine, media and journalism, law and finance and creative arts. LLMs are shifting from fun experiments to essential tools, saving people time and unlocking possibilities we hadn't imagined before. How did we get here? A brief history of LLMs. It's easy to think that LLMs just appeared overnight, but the journey has been decades in the making. The early days, rule-based systems. Before LLMs, AI language models were basically glorified if-then statements. Eliza, one of the earliest chatbots from the 1960s, could mimic a therapist by repeating your statements back at you. It felt conversational, but it wasn't thinking, it was following a script. Statistical language models, 1990s to 2010s. Things got better when researchers started using probability instead of hard-coded rules. This is where models like n-grams and hidden Markov models, HMMs, came in. Instead of a rigid script, they looked at the likelihood of one word following another based on real-world text samples. This led to major advancements in machine translation, speech recognition, and early chatbots. But these models still had limits. They couldn't understand long-term context. Ask them to generate a paragraph, and they'd lose track of what they were saying halfway through. The Deep Learning Revolution, 2013 present. This is when everything changed. 2013, Word2Vec introduced word embeddings, a way for computers to understand the relationships between words. Suddenly, an AI could know that king and queen are related concepts. 2017, the transformer architecture was introduced in the paper attention is all you need. This was the big bang moment for modern LLMs. Transformers made it possible for AI to process entire sentences, or even whole books, at once instead of word by word. 2018 now, BERT, GPT-3, ChatGPT, and GPT-4 took AI language models to the next level, making them capable of answering complex questions, generating essays, and even writing code. And the craziest part? We're still at the beginning. Basics of natural language processing. If large language models, LLMs, are the powerhouse of modern AI, then natural language processing, NLP, is the engine that makes them run. NLP is what allows machines to understand and generate human language in a way that feels natural. But let's get something straight right off the bat: machines don't understand language the way humans do. They don't have thoughts, emotions, or intentions. What they do have is an incredible ability to recognize patterns in vast amounts of text, and that's where the magic happens. So, let's break it down. How do machines break apart, analyze, and rebuild human language? Breaking language into pieces, tokenization, lemmatization, and stemming. Before an AI can process language, it needs to chop it up into manageable pieces. This is where tokenization, lemmatization, and stemming come into play. Tokenization, turning sentences into bite-sized chunks. Think of tokenization like cutting a paragraph into individual words or phrases. Instead of treating text as one long stream of characters, an AI first breaks it into tokens, which can be words, subwords, or even characters. For example, take this sentence: the quick brown fox jumps over the lazy dog. A word-based tokenizer might split it like this: the quick brown fox jumps over the lazy dog. But here's the problem: not all words stand alone. Some words are made of smaller meaningful parts, like don't, do, and, or running, run, ing. To fix this, LLMs often use subword tokenization like byte pair encoding, BPE, or word piece, which break down rare words into reusable parts. This helps AI handle new words it has never seen before. Lemmatization and stemming, finding the root meaning. Humans naturally understand that running, ran, and runs are variations of the word run. But a computer sees them as completely different words, unless we teach it otherwise. Stemming is the quick and dirty way of reducing words to their root by chopping off endings: running, run, happily, happy, study, studi. The problem? Stemming often butchers words into nonsense. That's where lemmatization comes in. Instead of blindly cutting words apart, it uses a dictionary to convert words to their proper root form. Running, run, happily, happy, study, study. This makes NLP models far more accurate when understanding word relationships, understanding meaning, syntax versus semantics. Once a model has broken a sentence into tokens, it needs to figure out what those words actually mean. This involves two main aspects of language: 1. Syntax, the structure of language, how words are arranged in a sentence. 2. Semantics, the meaning behind the words. Think about these two sentences: the cat sat on the mat. Makes perfect sense. Mat the on sat cat the. Nonsense, but the words are still there. Syntax tells us that the second sentence is wrong, even though it contains the right words. AI models use tools like part-of-speech tagging, POS, dependency parsing, and constituency parsing to recognize grammar rules. Semantics, on the other hand, is where things get tricky. Consider these two sentences: the bank was closed when I arrived. I swam to the bank of the river. Here, the word bank means two completely different things. Humans understand this instantly based on context, but AI needs statistical models and word embeddings, like word2vec or BERT, to figure it out. Context is everything. Context is what allows us to understand Apple as a fruit versus Apple as a company. Can you pass the context is what allows us to understand, can you pass the salt? A request versus yes, I can pass the salt. A statement. Earlier AI models struggled with context. For example, traditional chatbots forgot what you said after a few sentences. But modern LLMs, thanks to transformers and attention mechanisms, are able to remember the flow of a conversation, generate responses that actually stay relevant, understand subtle cues and implied meanings. This is why GPT-4 is so much better at keeping track of long discussions compared to early chatbots. Mathematical foundation of LLMs. Let's be honest, when people hear math, they either get a spark of curiosity or flashbacks to high school algebra trauma. But here's the twist: the math behind LLMs isn't some mystical black box, it's the secret sauce that powers everything. From autocomplete to ChatGPT. And don't worry, we're not diving into terrifying equations. This is about intuition. The why and how behind what makes these models tick. If LLMs were magic, this is the trick behind the illusion. Language as probability, the AI crystal ball. At the core of every language model is one question: given what I've seen so far, what word is most likely to come next? LLMs are probability machines. They're constantly guessing. After the cat sat on the dash, what's the most likely word? Is it mat, floor, roof? All of these are possibilities, but some are more likely than others. Enter conditional probability. The model doesn't see language like we do. It sees next word, previous words. It assigns a probability to each possible next word. Then, it picks one based on sampling strategy. We'll talk about that in a later chapter. If that sounds simple, it is. But doing this at the scale of entire books, conversations, and code bases? That's where things get wild. Vectors, the language of machines. Let's say you wanted a machine to understand that cat and dog are more similar than cat and refrigerator. How would you teach it that? You can't give it definitions or pictures. Instead, you give it vectors, mathematical representations of words. The word vector. Imagine every word is a point in a massive 300-dimensional space. In that space, king and queen are close to each other. Apple, fruit, is far from apple, company, and less context brings them together. Walking, ran, and jog all huddle in a fitness-themed neighborhood. These representations are called embeddings. Early models like Word2Vec made this idea famous by showing that relationships could be captured mathematically. King man plus woman is almost equal to queen. It's not memorizing, it's geometry. Probability meets vector space, how it all clicks. This is where LLMs become more than just math nerds. They take probability and combine it with vector representations of words, sentences, and entire contexts. That's right, not just individual words, entire meanings get embedded into high-dimensional space. Models like BERT or GPT convert your sentence into vectors, then use those to predict or generate text. Every word, phrase, or idea gets transformed into numbers, manipulated using linear algebra and calculus, and finally converted back into human-readable language. The result? You give it a prompt, it navigates this vast abstract space, and returns a response that feels like magic, but it's all just math. Linear algebra, the unsung hero. If you've ever heard someone mumble matrices and look the other way, now's your chance to redeem that moment. Because matrices are everything in LLMs. An LLM is built out of layers of transformations, where words are converted into vectors. Vectors are multiplied by matrices, think gigantic spreadsheets of numbers. The model learns which matrix combinations best predict language. These transformations allow the model to understand relationships, filter noise, and amplify important patterns. Every operation in a neural network, from attention mechanisms to backpropagation, is a clever application of matrix math. You don't need to multiply them by hand. Just know this: without linear algebra, your favorite AI wouldn't exist. Calculus, teaching the model to learn. Okay, so how do you train a model with billions of parameters? How do you make it better over time? You use calculus, specifically, gradients. Here's the idea. 1. The model makes a prediction. 2. You check how far off it was, using a loss function. 3. You use derivatives to figure out how to adjust the model's weights so it performs better next time. This process is called backpropagation, and it happens millions of times during training. Each time, the model gets a tiny bit smarter. The better it predicts, the lower the error. It's like teaching by trial and error powered by math. Understanding transformer architecture. If you've ever wondered what really made modern AI explode, this is it. Transformers are to LLMs what the engine is to a Ferrari. Without them, we're still stuck with chatbots that forget your name mid-conversation and models that can't finish a coherent paragraph. Before transformers, language models were like forgetful storytellers, okay with short phrases, but lost when you asked them to hold on to an idea longer than a few sentences. Then, in 2017, a paper called "Attention is All You Need" dropped, and the world of AI hasn't looked the same since. The problem: memory limits and sequential bottlenecks. Earlier models like RNNs, recurrent neural networks, and LSTMs, long short-term memory networks, were built to handle sequences. They took in one word at a time and updated their memory as they went. But here's the problem: they processed words sequentially, which made them slow. They had a hard time remembering stuff from far back in the text. Imagine reading a novel where your memory resets every page. You'd never finish the story. That was the RNN struggle. The breakthrough: attention mechanism. Instead of slogging through sentences word by word, what if a model could look at all the words at once and decide which ones actually mattered? That's the core idea behind attention. How it works: conceptually, let's say the model is reading, "The animal didn't cross the street because it was too tired." What does it refer to? The animal or the street? A good model needs to pay attention to the right words to understand meaning. The attention mechanism allows the model to weigh the importance of every word in a sentence relative to every other word. So when it gets to it, the model can go back and say, based on the context, I think it probably refers to animal. This attention score is calculated using vectors and dot products, the math from chapter 4, but the result is this: the model knows where to look when making predictions. Self-attention: the secret sauce. Now here's where things get clever in a transformer. Every word pays attention to every other word, even itself. This is called self-attention. So instead of just understanding a sentence in linear order, the model builds a web of relationships between all the words in a sentence simultaneously. This means, dog can relate directly to barked even if 5 words apart. He can connect back to Professor Jensen from earlier in the paragraph. That's how LLMs can keep track of meaning across longer distances in text, something RNNs and LSTMs seriously struggled with. Multi-head attention, parallel processing. Baby, now imagine trying to capture all kinds of relationships: subject-verb agreement, pronoun resolution, cause and effect. Trying to cram all of that into a single attention head would be overwhelming. So transformers use multiple attention heads. Each head looks at the sentence from a different perspective. One might focus on grammatical structure, another on positional cues. This is called multi-head attention, and it gives the model multiple views on the same input, all processed in parallel. Why transformers crush the competition? Here's why: the transformer design changed the game. No more bottlenecks. Words are processed in parallel, not one at a time. This makes training fast, really fast. Global context. The model doesn't forget what happened at the beginning of the sentence, it can access that info instantly. Scalable. The bigger the model, more layers, more heads, the better it performs. That's why GPT-3, GPT-4, and others get more powerful with scale. Transformers are modular, flexible, and massively efficient. You can stack layers, tweak heads, and scale them up to insane sizes. Which is exactly what we did. Putting it all together, anatomy of a transformer block. Let's break down what a single layer in a transformer looks like, and this is repeated dozens or hundreds of times in large models. 1. Input embedding, turn words into vectors. 2. Self-attention layer, every token looks at every other token. 3. Multi-head attention, multiple attention heads run in parallel. 4. Add and norm, combine outputs and normalize. 5. Feed-forward network, a little neural network gives it some extra brainpower. 6. Add and norm again, rinse and repeat. These blocks stack, passing more abstract representations up the chain. Early layers focus on basic structure, later layers understand high-level meaning, like, is this sarcastic? Or, does this sentence sound persuasive? Transformers today, the core of modern AI. Everything from BERT to GPT-4, Claude, Gemini, and Mistral, all of them are built on transformers. Even image and audio models are adopting this architecture. This design has become the foundation of almost every state-of-the-art AI system. If you've interacted with AI that felt shockingly fluent, chances are it was powered by a transformer. Training a large language model. Large language models don't just appear out of thin air, they are meticulously trained on massive amounts of data using powerful algorithms and infrastructure. This unit explores the entire pipeline behind making an LLM smart, starting with the vast oceans of internet text that serve as its training ground. We'll uncover how raw data is cleaned, tokenized into digestible chunks, and used to pre-train models through clever learning strategies like masked or causal prediction. As we move deeper, we'll see how general-purpose LLMs are fine-tuned for specific tasks, made safer through human feedback, and adapted to perform well with minimal additional training. We'll also look under the hood at the hardware needed to train these models, from GPUs to custom AI chips, and understand the enormous computational and ethical implications of scaling LLMs. Data collection and pre-processing. If the transformer is the brain of an LLM, then data is its lived experience. You can have the most brilliant architecture in the world, but without data, vast, diverse, high-quality data, it's nothing more than an empty skull. Training a large language model is less like giving it a textbook and more like dropping it into the middle of the internet and telling it, figure it out. But where does that data come from? How do we prepare it? And what should we not include? Let's walk through the raw, messy, fascinating world of data collection and pre-processing. Where do LLMs get their data? The short answer? Everywhere. The long answer? It's curated, scraped, filtered, and, hopefully, cleaned before it ever touches the model. Here are the big sources. Common Crawl, one of the largest public web archives, millions of web pages crawled every month. It contains everything from blogs and forums to Wikipedia clones and recipe sites. The upside: huge, diverse content. The downside: a lot of noise, spam, and low-quality junk. Wikipedia, a goldmine of structured, factual-ish information. It's clean, multilingual, and constantly updated. Every modern LLM includes Wikipedia in its training diet. Books, digitized books, both fiction and non-fiction, give models exposure to long-form, coherent thought. This helps with generating essays, storytelling, and structured reasoning. News articles provides current events, formal tone, and real-world facts, with some bias baked in, of course. Social media and forums, Reddit, Stack Exchange, etc. Informal, human, and full of dialogue, perfect for helping a model learn how people actually talk, not just how they write. But also a minefield of toxicity, bias, and misinformation. Code repositories. For code-generating models, sites like GitHub provide a rich resource of programming languages, software patterns, and comments. This is what enables models like Codex or GPT-4 to write functional code. Cleaning the data. Taking out the trash raw text scraped from the internet is a hot mess. It contains duplicates, spam, nonsensical HTML, offensive content, random tables, emojis, and footers from 2006. So before we even think about training a model, we need to filter the noise. Deduplication. If the same sentence appears 10,000 times, the model might overlearn it. So we remove repeated passages. Language detection. A model trained on English shouldn't be accidentally trained on pages of Russian or Hindi. Language detection filters out the wrong inputs. Content filtering. Offensive, violent, or abusive content needs to be removed or the model will reflect it. This isn't foolproof, and it's a major ethical concern we'll explore later. Boilerplate removal. Stripping out things like login, subscribe, cookie banners, and copyright disclaimers. These appear all over the web and serve zero purpose in language modeling. Document quality scoring. Some pipelines score documents based on clarity, structure, and grammar. Higher scores equals better training. Examples. Pre-processing. Getting text into shape. Once we've got clean-ish text, we still need to prepare it for training. This involves several key steps. Tokenization. We break text down into tokens, smaller units that a model can understand. You'll remember this from Unit 1. Advanced LLMs use subword tokenization like byte pair encoding, BPE, or unigram models, which help them generalize to new or rare words. Normalization. We unify text across sources. That means lowercasing, sometimes, removing special characters, converting emojis or accents, consistently standardizing punctuation. Sentence and document splitting. Text isn't fed into the model in giant blobs, it's broken into smaller, digestible chunks, like paragraphs, documents, or dialogue turns. Context windows matter. Alignment and labeling. For supervised fine-tuning, in later stages of training, especially fine-tuning, we may align questions with answers, or label data with tasks like summarization or translation. Tokenization and encoding before a language model can think, generate, predict, or even pretend to understand. It first needs to do something surprisingly tricky: break language into pieces it can actually read. That process is called tokenization, and it's more than just splitting sentences into words. It's about translating the slippery, messy world of human language into something that a machine can mathematically process. So how do we go from hello, world, to a string of numbers that a neural net can learn from? Let's find out. What is a token, really? Think of a token as the basic unit of meaning that an LLM operates on. It's not necessarily a word, it might be a character, a part of a word, or sometimes even punctuation. Take this sentence: unbelievably, the robot relearned dancing. Depending on the tokenizer, that might become word-based tokens, unbelievably, the robot relearned dancing character-based tokens, UNBEL. Subword tokens, believe, ably, the robot relearned dancing. So why not just use whole words? Because language is a minefield of misspellings, rare or made-up words, morphological variations, run, runs, running, ran, emojis, hashtags, URLs. If the model only learned words it had already seen, it would constantly break. That's where subword tokenization steps in. It breaks words into chunks the model has seen before, so it can generalize. By pair encoding, BPE, the crowd favorite, originally developed for text compression, BPE is now the go-to for most LLMs, including early versions of GPT. Here's how it works. 1. Start with characters as the basic tokens. 2. Find the most common adjacent character pairs, like T plus H, and merge them. 3. Repeat the process, merging the most frequent pairs, until you reach your desired vocabulary size. This results in a vocabulary that includes common full words, the, cat, robot. Useful subwords, ing, re. Flexible fragments that can be combined to form rare or unknown words. Why BPE works so well: it can handle new words by piecing them together from known parts. It strikes a balance between vocabulary size and granularity. It's efficient to store and compute. 3. WordPiece and Unigram language models. WordPiece, used by BERT, similar to BPE, but instead of blindly merging the most common character pairs, it chooses merges that maximize the likelihood of the training data. It's a bit more precise, especially for preserving semantic structure. WordPiece tends to be better at keeping subword units meaningful so you don't get bizarre or awkward splits like cathedral, cat, head, owl. Unigram language model tokenization. This method, used by models like XLNet and SentencePiece, starts with a large list of possible tokens and gradually removes the least useful ones. It's more probabilistic than greedy. Unigram models often result in more compact, optimized vocabularies, great for multilingual models or compact LLMs. Encoding, turning tokens into numbers. Once the text is tokenized, it's still just a list of words or subwords. But models don't understand words, they understand vectors. So, we map each token to a unique ID. For example, hello 1541 world 8427 ! 993. This sequence of integers becomes the input to the neural network. From there, the model uses embeddings, you might remember those from Chapter 4, to turn each number into a rich vector representing meaning, context, and usage. Why tokenization strategy matters: use too large tokens, and the model struggles with rare words. Use too small tokens, like individual characters, and the model gets bogged down in length and loses semantic meaning. Use the wrong strategy for a language, and your model might completely miss key patterns, e.g. suffixes in Finnish or agglutination in Turkish. Example, let's say you want to tokenize the word unhappiness. A naive tokenizer might treat it as one rare word and fail to generalize. But a smart subword tokenizer would split it into unhappiness, which means the model understands the mood of the word, even if it's never seen unhappiness before. What happens when it breaks? Tokenization is also where weird bugs and hallucinations can creep in. A model might tokenize Jason Bourne as Jason, Boar, NE, making it sound like a medieval knight. Emojis, hashtags, and creative spelling can throw off even smart tokenizers. Slight misspellings, definitely, may result in bizarre splits and misinterpretation. That's why modern LLMs constantly experiment with better tokenization schemes, more adaptive, more inclusive, and better at handling real-world text. Pre-training LLMs so you've got a mountain of clean, tokenized, encoded text. The architecture is in place. The stage is set. Now what? Now comes pre-training, the process that transforms a blank slate neural network into a language-savvy machine that can write novels, summarize research, and hold convincing conversations. If training an LLM were a movie, this is the montage scene: millions of documents, billions of tokens, and thousands of GPUs humming in sync as the model learns everything it possibly can about how language works. What is pre-training, really? Pre-training is the first and most crucial phase in building an LLM. It's where the model learns to predict text using nothing but patterns it uncovers in massive corpora without any human-labeled data. We don't tell it the answers. We don't give it grammar rules. We simply say, here's a bunch of language. Learn to guess what comes next. And astonishingly, that's enough. 2 ways to pre-train, MLM versus CLM. There are 2 dominant approaches to pre-training a language model. Each one defines how we make the model learn. Masked language modeling, MLM, used by models like BERT. This strategy hides words in a sentence and asks the model to fill in the blanks. The quick brown mask jumps over the lazy dog. This teaches it to understand relationships in both directions, what came before and after. White heavy checkmark, great for understanding language, classification, question answering. Crossmark, not great for generating fluent text, since it doesn't learn to write left to right. Causal language modeling, CLM, used by models like GPT. This approach trains the model to predict the next token in a sequence. The quick brown fox jumps over the lazy. The model predicts dog. This mirrors how we naturally write or speak one word at a time, left to right. White heavy checkmark, great for generating coherent, creative text. Crossmark doesn't see the future, so it struggles with bidirectional context. The engine under the hood, loss functions. To teach a model, we need feedback. How do we know it's learning? We use a loss function, which tells us how far off the model's predictions were from the actual answer. Think of it as the "you're getting warmer" meter. Cross-entropy loss, this is the gold standard for LLM training. It measures how likely the model thought the correct token was, and penalizes it if it was too confident in the wrong answer. If the correct next token is dog, but the model thinks it's frog, it gets punished accordingly. The goal? Minimize loss across billions of predictions. As the model trains, it slowly starts assigning higher probability to the right tokens and lower to the wrong ones. That's how it gets smarter. Negative log likelihood, NLL. A loss in disguise. NLL is just another way of expressing cross-entropy. It measures how surprised the model was when the correct answer appeared. Low surprise equals good, high surprise equals bad. They're mathematically equivalent, but the NLL framing helps us think about uncertainty. We don't just want the model to be right, we want it to be confident and calibrated in its rightness. Unsupervised, yet powerful. Here's what's wild. Pre-training uses no explicit labels. No human annotators. No task-specific data. It's self-supervised. The model teaches itself by guessing missing or next words and checking how wrong it was. And by doing this billions of times across massive datasets, it learns syntax and grammar, common knowledge. Paris is in France, water is wet, writing style, tone, formality, even subtle things like sarcasm, rhyme, or rhythm, all without being told anything. Scale is everything. There's a recurring theme in LLMs: more data, bigger models, longer training equals better results. GPT-2, 1.5B parameters, was impressive. GPT-3, 175B, blew it out of the water. GPT-4? Rumors say it's bigger, deeper, and more nuanced. Why? Because language is complex, and the more a model sees, the better it gets at generalizing. The law of large numbers becomes a philosophy. Scale unlocks ability. The cost of intelligence. All this pre-training comes at a cost, a massive one. Millions of GPU hours, huge energy footprints, gigabytes of memory across thousands of processors, training runs that can take weeks or even months. This is why LLMs are so expensive to train and why pre-training is usually done once. Afterward, models are fine-tuned on specific tasks. We'll get to that in Chapter 9. Fine-tuning and transfer learning. Pre-training gives a language model its voice. It learns how grammar works, what makes a sentence flow, how words relate. But pre-training alone doesn't teach it to answer legal questions, write medical summaries, or handle customer service chats. To get there, we need to refine it, shape it, specialize it. Enter. Fine-tuning, the process of taking a pre-trained, general-purpose LLM and tailoring it for specific skills, domains, or behaviors. This is where your friendly, all-purpose LLM becomes a doctor's assistant, a programmer's co-pilot, or a polite customer service bot. What is fine-tuning? Fine-tuning is the process of continuing training on a smaller, task-specific dataset after pre-training is complete. The base model already knows how to use language, it just needs a nudge in the right direction. For example, you want your model to write financial reports? Fine-tune it on financial data. Need it to answer questions about medieval history? Fine-tune it on historical texts. Want it to follow instructions politely? Fine-tune it on examples of polite interactions. The idea is to take what the model already knows about language and align it with the behavior or domain you want. Transfer learning. Don't start from scratch. Fine-tuning works because of transfer learning. This means knowledge learned in one domain, language structure, general knowledge, transfers well to another domain, specific tasks. Without transfer learning, you'd need to train a model from scratch every single time, which is wildly expensive and unnecessary. Think of pre-training as teaching a model how to read and write. Fine-tuning is teaching it what to write in a given situation. 3 levels of adaptation. Depending on how much data, compute, and control you have, there are multiple ways to adapt a model to new tasks. Zero-shot learning. You don't fine-tune the model at all. Translate this sentence to Spanish. I love learning. The model figures it out because it's seen lots of similar patterns before. Works surprisingly well, especially with large models trained on massive datasets. Few-shot learning. You give the model a few examples in the prompt to guide its behavior. Translate to Spanish. I love learning. Me encanta aprender. She runs fast. Ella corre rápido. Cat sleeps all day. This nudges the model toward your intended task without changing its internal weights. Great for quick adaptations, but still limited by context length. Full fine-tuning. This is the real deal. You continue training the model using labeled examples of a specific task. Show it thousands of pairs of input, desired output, let it adjust its internal weights to improve performance on that task. This approach gives you maximum control, but it also requires training infrastructure, high-quality data, careful hyperparameter tuning used when precision, tone, or safety matter a lot, e.g. healthcare, law, customer-facing apps. Reinforcement learning from human feedback, RLHF, this one's a game-changer. It's how models like ChatGPT learn to be helpful, honest, and harmless. Here's the process. Start with a pre-trained model. Ask it to generate several possible answers to a prompt. Have humans rank the outputs from best to worst. Train a second model to predict those rankings. Use that signal to fine-tune the original model using reinforcement learning. The result? A model that not only knows language, but learns to behave like a helpful assistant. RLHF adds a human layer to the training process, aligning models not just with data but with values. Alternatives to full fine-tuning, lightweight approaches. If you don't want to retrain the entire model, which can be slow and expensive, there are lighter options. Adapter layers add small, trainable modules inside the frozen model. Only train those. Faster, cheaper, and still surprisingly effective. LoRA, low-rank adaptation, a clever trick. Inject small matrices into the attention mechanism and only train those. LoRA is memory efficient, fast, and used heavily in open-source fine-tuning efforts. Prompt tuning and prefix tuning. Train a custom prompt or prefix that conditions the model to behave a certain way. Great when you want to guide behavior without touching the model weights. Why fine-tuning can go wrong. Fine-tuning is powerful, but it's easy to mess up. Overfitting. The model memorizes your dataset and fails to generalize. Catastrophic forgetting. It gets so focused on the new task that it forgets general language skills. Bias amplification. If your fine-tuning data is biased, your model will double down on it. Fine-tuning isn't just technical, it's also ethical. The data you use shapes the model's behavior, tone, and worldview. Hardware and compute for LLM training. Let's get one thing clear. Training a large language model is not like running a few lines of code on your laptop. It's a massive, industrial-scale operation, the AI equivalent of launching a rocket. You're dealing with billions of parameters, trillions of data tokens, and training runs that can last weeks across thousands of machines. LLMs don't just need good code, they need serious horsepower. Greedy search, the safe and boring option. The most basic strategy is greedy decoding. The model always chooses the token with the highest probability. Example input: once upon a top predictions, time 0.45, dream 0.30, kingdom 0.10, greedy search picks, time. Sounds logical, right? But there's a problem. Greedy decoding often leads to dull, repetitive, and predictable responses. Try it on long text and you'll get loops. The cat is on the mat. The cat is on the mat. Repetition, no creativity. Greedy decoding is like always playing it safe in conversation. Technically correct, but lifeless. Beam search, smarter, but still rigid. Beam search tries to be more strategic. Instead of just picking the best word each time, it explores multiple paths in parallel, keeping the top and most promising sequences. The beam, it's like saying, let me follow the 5 best storylines at each step, and pick the best one at the end. This works well for structured tasks like translation or summarization, where accuracy matters more than creativity. But again, beam search often feels formulaic. It's great for tasks with a clear correct answer but less so for open-ended generation. What if you want the model to loosen up? To take risks? That's where temperature comes in. Temperature is a knob you can turn to control the randomness of the output. Low temperature, less than 0.7, conservative, focused on high probability tokens. High temperature, greater than 1.0, risk-taking, will explore less likely options. At temperature equals 0, the model becomes greedy. At temperature equals 1, it samples according to the true probabilities. At temperature equals 2, things start getting weird. It's like adding personality. 0.3, robot librarian. 0.7, balanced storyteller. 1.5, drunk poet at a jazz bar. Top K sampling, controlled creativity. Instead of sampling from every possible token, top K sampling narrows the field. You set K equals 50, and the model picks randomly from the 50 most likely tokens. Everything else? Thrown out. This forces the model to stay reasonably grounded, while still injecting variation and creativity. Top K keeps the wild stuff in check, without falling back into the trap of repetitive predictability. Nucleus sampling, top P. The Goldilocks strategy. If top K is fixed width, top P, also called nucleus sampling, is adaptive. Instead of always keeping the top 50 tokens, the model dynamically selects the smallest set of tokens whose combined probability adds up to P. Example: 0.9. This gives you more flexibility, better balance between randomness and relevance, cleaner outputs, and longer text. Top P is what most modern LLMs use by default. It's the sweet spot between coherent and creative. Hybrid strategies. In practice, you'll often see temperature plus top K or temperature plus top P. These combos offer a creative engine, temperature, a safety net, top K or top P. Fine-tuning these parameters lets you shape the model's vibe. Wanted to write like a lawyer? Lower temperature, narrow P. Wanted to write poetry? Higher temperature, wider P. Sampling strategies shape personality. You can take the same prompt and completely change the tone just by tweaking how the model samples. Prompt: she opened the door and saw, greedy, her mother standing there. Top K, a shadow flicker across the floor. Top P, high temp, a flamingo in a top hat juggling clocks. Same model. Wildly different outputs. Sampling is what gives the model style. Prompt engineering and input conditioning. You could give an LLM the same model weights, same training, same everything, and yet get vastly different results depending on how you phrase the prompt. That's the magic and madness of prompt engineering. This chapter is all about talking to the model in a language it actually understands. The model isn't psychic, it's just really, really good at responding in context. And context, as you'll soon see, is everything. Why prompts matter. LLMs don't think, they react to input. That means the way you phrase your prompt directly shapes the output. Let's say you ask, write a summary of the Industrial Revolution. You'll get a neutral, textbook-style summary, but now try, explain the Industrial Revolution to a 10-year-old. Now you get short sentences, simple metaphors, and relatable examples. Change it again. Summarize the Industrial Revolution in the tone of a pirate. Suddenly you're reading about steamships and textile mills through the lens of progress be comin' with iron wheels. The prompt frames the task, tone, audience, structure, and the model will lean hard into those cues. The art of prompt engineering. Prompt engineering is the practice of designing inputs that guide the model toward better, more reliable, or more creative outputs. It started as a kind of hacking, people experimenting with wording. Now it's becoming a critical AI skill. Effective prompt design can improve answer accuracy, reduce hallucinations, enforce structure and formatting, control tone, persona, or role, trigger complex reasoning. Prompt structures that work. Prompt structures that work. Here are a few techniques that dramatically improve LLM performance. A. Instructional prompts tell the model exactly what you want it to do. Summarize the following text in bullet points. Write a step-by-step explanation of this code. Give me a list of 3 pros and 3 cons. LLMs are very literal. If you're vague, they'll guess. Role-play prompts. Ask the model to take on a specific role. You are a friendly chemistry tutor. Explain ionic bonding. Act as a sarcastic film critic reviewing Cats, 2019. This sets tone, voice, and behavior all with one sentence. Few-shot prompts. Give the model a few examples to show the task structure. Input, translate to French English, hello French, bonjour English, goodbye French, au revoir English, thank you French. This is called in-context learning, and LLMs are remarkably good at it. The more examples you provide, the more accurately they mimic the pattern. Chain of thought prompting. This technique encourages step-by-step reasoning instead of jumping straight to the answer. If there are 3 apples and each person takes one, how many are left? Let's think step by step. The model starts explaining its reasoning before outputting the answer, which leads to better logic, especially for math and logic puzzles. Even just adding "let's think step by step" dramatically boosts accuracy on reasoning tasks. Advanced prompting tactics. A. Self-consistency. Run the same prompt multiple times with different sampling, example. Top P, and aggregate the results. Often used in zero-shot reasoning. React prompting. Combine reasoning and action. The model explains what it's doing while using external tools or querying APIs. Useful in agent-style systems. Instruction tuning. This isn't prompting per se, it's training the model on lots of prompts and desired completions, so it performs well on new instructions out of the box. How ChatGPT and Claude work. But the concept emerged from the same space. Prompt failures, when things go sideways. Prompting is powerful but fragile. Small changes in wording can yield nonsensical outputs, hallucinations, wrong tone. Irrelevant answers. Translate this to Shakespearean English. Good, make this more Shakespeare. Weird metaphors and dramatic pauses, but not quite right. You're not just giving instructions. You're programming behavior using natural language, and natural language is full of ambiguity. Prompt engineering as UX design. Think of the prompt as the user interface to the model's brain. A bad prompt is like clicking the wrong button in an app. A great prompt? That's a seamless, intuitive experience where the AI just gets what you want. Prompt engineering is now a key skill for product designers, writers and marketers, researchers and educators, developers building AI apps. As models get stronger, this skill doesn't go away, it just evolves. Memory and long context understanding. Language isn't just a string of sentences, it's a web of references, callbacks, nuance, and continuity. Understanding a single paragraph is one thing. But understanding an entire conversation, legal document, or novel? That's something else entirely. LLMs may seem smart in the moment, but ask them to remember what you said 3,000 words ago and suddenly, the brain fog sets in. Welcome to the frontier of long context understanding, where memory, architecture, and clever workarounds determine how far an AI's attention can really stretch. The context window, a built-in limit. Every LLM operates within a context window, the number of tokens it can see at once. Think of it like the model's short-term memory. For example, GPT-2, 1024 tokens, less than one chapter of a book. GPT-3, 2048 tokens. GPT 3.5, 4096 tokens. GPT-4, 8K and 32K versions. GPT-4 Turbo, 128K tokens, roughly a 300-page book. Everything inside that window? The model can read, reference, and reason over. Everything outside that window? Gone. Forgotten. Irretrievable. If you've ever had a chatbot lose the thread halfway through a long conversation, that's the context limit at work. Why long context is hard for transformers. The issue isn't just memory size, it's how attention mechanisms work. Transformers calculate attention between every pair of tokens. That means, for n tokens, there are n superscript 2 relationships. Doubling the input length doesn't double the compute, it quadruples it. So going from 2K to 128K context isn't a linearly bigger model, it's a computational monster. That's why long context models require special tricks. Rope, alibi, and attention tricks. Researchers are inventing new techniques to stretch attention further, without collapsing under compute load. Here are a few. Rope, rotary positional embedding. Traditional transformers don't know the order of words, so we embed positions, token 1, token 2, etc. Rope does this using rotational math that helps preserve distance even in long sequences. It's used in models like GPT-4 and Claude. Alibi, attention with linear biases. Instead of absolute positions, alibi gives the model a bias toward nearby tokens. Think, pay more attention to recent things. It allows attention to extend to long sequences, but with a diminishing priority. Sliding window and chunked attention. These techniques split long text into overlapping chunks and process them in windows like reading through a document in sections. The challenge? Stitching those chunks back together coherently. This works better for summarization than for tasks requiring global coherence. External memory. Teaching models to remember. Some research goes beyond the context window entirely by giving LLMs external memory. Think, a database. The model can look things up in a long-term memory store, it can reference throughout a chat summaries of previous context, it can revisit on demand. These aren't part of the model's weights, they're dynamic memory systems. Think of them like notebooks the model can carry around. Popular approaches: retrieval augmented generation, RAG, memory-augmented transformers. Hierarchical context chunking. LLMs don't have memory like humans, but they can be given tools to fake it. Compression and summarization as memory hacks. When full memory isn't an option, we can compress. Some systems summarize older parts of a conversation, distill key facts, and refeed them into the prompt. Drop irrelevant sections to preserve space. It's like reading the cliff notes of your own conversation just to keep the thread alive. Downside? Compression can lose nuance. And bad summarization leads to garbled context. Why long-term memory is the future. As LLMs become more like assistants, researchers, or creative partners, they need to remember more than just the last few paragraphs. They need persistent memory across sessions, a sense of conversation history, the ability to refer to earlier ideas, styles, or constraints. That's why future LLMs are heading toward hybrid architectures. Neural models for reasoning. External memory for recall. Retrievers for precision. Basically, brains plus notebooks plus encyclopedias, all working together. Building and deploying LLMs. Training an LLM is only half the journey. Bringing it into the real world is where things get truly exciting. This final unit is all about how to build, deploy, and scale large language models in practice. Whether you're working on a hobby project or building enterprise-grade AI systems, this unit equips you with the practical know-how to go from a trained model to a fully functional application. We start with the fundamentals of training small-scale LLMs, covering dataset selection, architectural choices, and running training jobs in the cloud. From there, we explore deployment strategies, whether through APIs for easy integration or optimized on-device deployment for real-time use on edge devices. You'll learn how to improve inference speed, handle high-traffic applications, and compress models using techniques like quantization and distillation. We also weigh the trade-offs between open-source and proprietary models, examining tools from OpenAI, Meta, Mistral, and Hugging Face. Training a small-scale LLM from scratch. By now, you've explored the magic of how large language models work, how they're trained, and how they're used. But what if you wanted to build your own? Not a trillion-parameter GPT behemoth, but a small, lean, purpose-built LLM, something that runs on a few GPUs, or even a beefy laptop, trained on your own dataset, for your own use case. This is your practical blueprint for doing exactly that. Step 1. Define the scope first. Get clear on what you're building. Because trying to train your own GPT with limited compute and no plan? That's a recipe for disaster. Ask, what's the domain? Medical? Legal? Chatbots? Literature? How big does it need to be? Millions of parameters? Tens of millions? What languages will it support? What will it be used for? Answering questions, generating summaries, writing in a specific style? The clearer your use case, the more efficiently you can design your training pipeline. Step 2. Data collection and pre-processing. This isn't about massive web-scale scraping. It's about focused, high-quality datasets. Public domain books, Project Gutenberg. GitHub repos, for coding LLMs. Research papers, for academic assistance. Customer support transcripts. Domain-specific documents. Start with a modest dataset, a few hundred megabytes to a few gigabytes. Then, clean the text, remove HTML, broken encodings, etc. Deduplicate and standardize formatting. Tokenize using your chosen tokenizer, e.g. GPT-2 tokenizer, sentence piece. Save it in an efficient format, e.g. .song, .records, or PyTorch datasets. Remember, good data beats big data. Step 3. Choose your model architecture. You don't need to invent anything new. Use an off-the-shelf transformer model. Great starting points. NanoGPT, GPT-Neo, Eluther AI. Distill GPT-2. Tiny Llama/Pythia. Transformer from Hugging Face's Transformers library. Choose the number of layers and hidden size based on your GPU/TPU memory, your dataset size, your time budget. Example. A 6-layer transformer with 10 million parameters can be trained on a single GPU in a few days with the right setup. Step 4. Set up training infrastructure. Even small models need decent compute. You'll need GPUs, A100, B100, 3090, etc., or TPUs. A deep learning framework, PyTorch or TensorFlow. A logging system, weights and biases, TensorBoard, or even basic CSVs. Checkpointing. Save your model periodically to avoid losing progress. Use mixed precision training, FP16, to save memory and speed things up. Frameworks like DeepSpeed, Accelerate, or LoRa can help you go further on limited hardware. Step 5. Train. Start small, use a small batch size and learning rate. Monitor loss curves. Evaluate on held-out validation data. Your goal isn't state-of-the-art performance, it's a stable, coherent language model that learns something useful from your data. Training might take a few hours for a tiny model on a small dataset. A few days for a medium model with serious compute. Keep expectations realistic. The goal is understanding and utility, not outperforming ChatGPT. Step 6. Evaluate and iterate after training. Run some prompts through your model. Compare responses to your expectations. Check for repetition, hallucination, or nonsense. Fine-tune your tokenizer, loss function, or learning rate if needed. You can also fine-tune further using supervised fine-tuning. RLHF on a microscale. Human feedback. Deployment comes later. Don't rush it. Don't worry about APIs, containers, or web apps just yet. Focus on training something worth deploying first. Once you have a working model, you'll move into optimization and deployment, covered in next chapter. Deploying LLMs efficiently. You've trained a model. It works. It's spitting out coherent, task-relevant responses. Now comes the real-world test, putting it into users' hands. Deployment is where theory meets scale. The best model in the world won't matter if it's too slow to respond, too expensive to run, or too hard to integrate into real applications. Two primary deployment modes: API-based deployment, cloud-hosted. This is the most common setup. You host your model on a server, and applications interact with it via API calls. White heavy checkmark pros, centralized control and updates. Easy to scale with cloud infrastructure. Monitor usage, latency, logs, and health. Cons, limited memory and compute. Needs heavy model compression or distillation. Harder to update or patch. Great for mobile apps, private tools, embedded systems, wearables. Will dig deeper into edge deployment in Chapter 23, but just know, tiny models can go far with the right optimizations. Inference optimization, speed versus cost. You've trained the model, but now it needs to run fast and cheap, especially if you're serving thousands of users. Key techniques. Quantization reduces the precision of model weights, e.g. FP32int8, shrinking memory usage and speeding up computation with minimal loss in quality. Model pruning removes low-importance weights or neurons. Less compute equals faster inference. Distillation: train a smaller model, student, to mimic the output of a larger one, teacher. The smaller model is faster, and good enough for many real-world tasks. Batching: process multiple requests at once to improve GPU/TPU utilization. Helps reduce per-request latency at scale. Caching: store common prompt response pairs, example. FAQs, to skip repeated computation. Serving infrastructure choices: options include Hugging Face inference endpoints, ONNX runtime or TensorRT for optimized inference. Fast API plus PyTorch/TensorFlow backend VLLM or TGI, text generation inference, for large-scale serving use. Kubernetes or serverless solutions if you expect autoscaling demand. Keep in mind, load balancing. GPU scheduling. Model sharding, for big models across multiple GPUs. Secure APIs and rate limiting. Use tools like Prometheus plus Grafana. Sentry. Weights and biases. Custom dashboards: logs aren't just for debugging, they're your feedback loop for improvement. Cost management. Stay smart. Compress the model limit. Max tokens per generation. Use tiered pricing if you're offering access cache. Aggressively consider offering lightweight models for common tasks, and reserving the full model for premium use cases. Smart engineering equals sustainable scaling. Safety and abuse prevention. If you're deploying publicly, expect misuse. Mitigate with input filtering, prompt injection, jailbreaking, output moderation, toxicity, bias, hallucination detection. Rate limiting and abuse detection. Guardrails, stop words, blacklist/whitelist terms. Safety triggers. Also consider user reporting mechanisms, so people can flag harmful or incorrect output. Deployment isn't done, it evolves. Once the model is live, monitor continuously. Retrain or fine-tune based on user feedback. Update your datasets as language and usage evolve. Prepare to patch bias, drift, or hallucination issues on the fly. LLM deployment is a living process, not a final product. Running LLMs on edge devices. What if your AI could work without calling the cloud? No latency, no internet dependency, no sending data off device, just pure, local intelligence. That's the promise of on-device, edge, LLMs. But fitting a language model onto a smartphone or embedded system isn't just plug and play. It takes clever engineering, model compression, and hardware-aware design. Why run LLMs on the edge? Benefits: low latency, instant response, no round trips to the server. Offline access, use cases in remote locations or on planes, ships, and battlefields. Privacy preserving, sensitive data never leaves the device. Cost control, no API calls equals no cloud bills. Challenges: limited RAM and compute. Battery life constraints. Tiny storage space. Real-time performance expectations. This isn't about scaling up. It's about scaling down without losing the model's soul. Compression techniques, shrinking the model brain to run LLMs on device. We need to drastically reduce their size and resource needs. Quantization reduces the precision of model weights. FP32, FP16 or INT8 shrinks memory use and speeds up inference. Slight loss in performance, often unnoticeable. Most on-device models use 8-bit quantization or even 4-bit for ultra-low-end devices. Pruning removes unimportant neurons or connections. Think of it as trimming the fat, keeping the important weights and tossing the rest. 2 types. Structured pruning removes entire layers or channels. Unstructured pruning removes individual weights. Knowledge distillation. Train a smaller student model to mimic the behavior of a larger teacher model. Student learns to approximate outputs, patterns, and attention at a fraction of the size. This is how Tiny Llama, Distilbert, and MobileBert were born. Weight sharing and low-rank approximations. Techniques like LoRa, low-rank adaptation, allow fewer parameters to do more work, reducing memory footprint without retraining the whole model. Lightweight models for on-device AI. You don't need GPT-4 to run smart features on a phone. These compact models are designed for mobile and edge. DistillGPT-2/Distilbert, smaller, faster versions of BERT and GPT. Tiny Llama 1.1b, highly optimized LLM-based model. Phi-2 1.3b, small but powerful Microsoft model. MobileBert, specifically built for smartphone inference. Gemma 2b, with quantization, good for chat, summarization, and code. Paired with quantization, these can run on smartphones, Snapdragon, Apple Silicon, etc. Laptops. Raspberry Pi class edge boards. IoT and embedded systems. Frameworks and tools for edge inference. You'll need software optimized for small devices and efficient compute. Top tools: ONNX Runtime Mobile, TensorFlow Lite, PyTorch Mobile, ggml/llama.cpp, run LLM-like models on CPU using quantization. MLC LLM, compile LLMs for mobile GPUs, iOS, Android. Core ML, Apple, deploy optimized models on iPhones and Macs. Use cases of on-device LLMs. Real-world examples. Keyboard suggestions and autocorrect, Gboard, SwiftKey. Offline voice assistants, Pixel, Alexa on-device. Medical devices with privacy-sensitive inputs. Smart wearables with context-aware prompts. Augmented reality apps that need fast, local response. Trade-offs: what you gain and what you lose. Gain, speed. Privacy. Autonomy. Lower cloud costs. Lose, general knowledge, limited by training set size. Creativity and nuance, smaller models equals less expressiveness. Continuous learning, no real-time updates unless synced. Memory span, limited context window. The key is matching model capability to your use case. You don't need a 175B parameter model to correct someone's spelling. Building an LLM-powered chatbot. Time to roll up your sleeves. You've learned how LLMs work, how they're trained, optimized, deployed, and run at scale or on-device. Now let's build something real, a fully functional LLM-powered chatbot ready to run in a web app. This project ties together everything we've covered and shows how to turn all that theory into a real-world, interactive product. Define your chatbot's purpose before you code. Get clear on what your chatbot is for. Customer support assistant? Study buddy for high schoolers? Legal Q&A bot? Domain-specific guide, e.g. finance, healthcare, travel? This will shape everything: the dataset, prompt design, tone, safety filters, and deployment. Choose the model backend. Pick your LLM, locked proprietary API, easy mode. OpenAI, GPT 3.5/GPT-4 via OpenAI API. Anthropic Claude. Cohere. Google Gemini, great for quick startups and powerful responses. Just bring your API key. Open source model, self-hosted Mistral 7b/TinyLlama/Gemma/Phi2. Serve with llama.cpp, Hugging Face transformers, or VLLM requires a local or cloud GPU, but gives you full control and privacy. Set up your environment. Backend stack, Python, FastAPI or Flask. OpenAI, transformers, or Llama CPP Python. Unicorn or Unicorn for serving. Frontend stack, HTML/CSS/JavaScript. Optional, React or Vue for fancier UI. Chat UI components, React Chat widget, Bot UI, or build your own. Implement input filtering and prompting. You can't trust users to be nice. And you can't trust LLMs to always respond safely. Add input validation, strip prompt injection attempts, e.g. ignore previous instructions. Length limits, prevent abuse via massive inputs. Prompt wrapper, frame the model's role and tone. Example system prompt: you are a polite and helpful customer support agent for Acme Corp. Answer only questions related to our products. Add conversation memory, optional, for simple bots. Just keep the last message or two for more advanced bots. Use session storage to preserve chat history. Truncate older messages to stay within the model's context window. Summarize previous turns if context length is tight. Test your bot's behavior. Check accuracy, tone and helpfulness. Hallucination rate. Robustness against misuse. Example. Jailbreaking prompts. Tools like PromptFu, Langsmith, or Weights and Biases can help track prompt performance. Deploy to the web options, Render, Railway, Versal, Heroku, for front-end plus back-end. Docker plus Cloud GPU, e.g. Paperspace, Lambda Labs, for self-hosted models. Gradio/Streamlit for quick demos, especially if you're using Hugging Face models. Secure your API keys, rate limit your endpoints, and add logging. Add Polish, extras that make a difference: loading animations and typing indicators. Avatar icons or branding. Session storage for conversations. Export chat history. Toggle between models or personalities. This is where everything clicks. You've gone from understanding the internals of LLMs to building your own chatbot, from scratch or via API, and serving it to users. Whether it's for education, business, art, or fun, you now have the skills to bring AI into the real world. Now go build.
Ready for more mind-expanding lessons, interactive quizzes, and hands-on courses? Head over to brainyjuice.com. Your passport to a world of knowledge. Whether you're diving into engineering, exploring computer science, or delving into medical and biological sciences, Brainy Juice is the one-stop destination for curious minds. From mechanical and civil engineering to zoology and botany. From rocket science to terraforming planets. From ancient civilizations to modern history. From astronomy to full-scale physics. We've curated courses that cater to every passion and every goal. Each course is carefully designed by experts, packed with engaging lessons, real-world examples, and interactive quizzes. Push your limits by exploring over hundreds of topics. We're constantly expanding, so your thirst for learning never goes unquenched. Our platform is simple. Log in, pick a subject, and dive in. Go beyond the ordinary. Challenge yourself, master new skills, and fuel your curiosity with Brainy Juice. It's time to expand your horizons, because knowledge is the spark that ignites success. We'll see you in the next one.